Hey folks, I'm going to go over some of the most missed questions in the chapter 25-26 test. Um, so I'm just going to go in order and talk kind of work them out very basically for you. Um, no, she's not having a bad hair day. Most of you got that one right, thankfully. All right, let's start with number 8. So for number 8, uh, 20 of us got this right. There were 61 people took the test. So they give you 4-point charges, and they say that they give you Q, and we're going to have different numbers. So they gave me a Q, and they gave me the side of the square. They said determine the work to assemble this charge distribution. So we did do this in the notes, and this was also in a couple of your RPs and on the review packets, but I'll go over it one more time. So to put the first charge in empty space is going to take no work at all. So that's just going to be 0. Okay. Plus, to put that second charge there, okay, the first charge is going to make a voltage, which is KQ over A, and then times the second charge we're putting there, so that's Q. So that's QV, okay, or V times Q. So our first charge was a free ride. Our second charge, you had to fight against that voltage. For the third charge, I'll make that one down here. It is A away from the second charge and A root 2 away from the first charge. So we've got the first charge makes a voltage KQ over root 2A, plus the second charge makes a voltage down there of KQ over A. And I got to take all that times the Q I'm sticking there. That's Q3. All right. And then plus, and then Q4. Okay. So Q1 and Q3 are each going to make a voltage of KQ over A there. So I'm just going to take that times 2. Plus Q2 is going to make a voltage of KQ over root 2A. All right, and that's all times Q. Okay. Now, at this point, if you wanted to, you could plug in numbers. I found it easier to take out the K. It's Q times Q everywhere, so it's Q squared over A, and then I just added like terms. So the ones that don't have a square root of 2, there's 1, 2, 3, 4. So there's 4 of those. The ones that have a square root of 2 on the bottom, how many of those are there? 1, 2, so 2. So that's another, so you can just plug in the K, Q, and A in your calculator one time and get that. So, but again, you could just plug and chug up here and that's fine, but it might be easier to do that. Okay. For number 10, looks similar picture, right? But different question. 10 asks, what's the voltage at the center of this square? Okay. So this is number 10. Okay, now by the way, 29 of us got that right. So about half of you got that right. Well, each charge is what's the distance from here to here? Well, this distance would be root 2a. Okay, from here to here, it'd be half that. So that's our distance. All 4 charges are that distance away. So the voltage would be 4 times KQ over root 2a over 2. And then I'll move that 2 to the numerator. And so you would get 8KQ over root 2A. So then you just plug in whatever value they give you for Q and for A in meters. So like A is 3 centimeters, that's 0.03 meters. And there you go. That would give you your right answer. Number 11 was missed frequently. 19 of us got that right, so only about a third. Let me go over to the number 11. So they're moving a little charge from out here to the center of the sphere. So the shell or the sphere is making the voltage that we're working against. So work equals Q delta V. So Q is a little q that we're moving, which in my example here is 2 microcoulombs, delta V. So we got to figure out delta V. Well, if you're outside the ball, I'll put, actually better yet, V outside. It's just going to be KQ over R. It's a symmetrically spherical charge. If you're outside of it, it's KQ over R. V inside is going to equal what? That's the key here. Well, if you're anywhere in here, the electric field is 0. So the field stops changing at the very surface right there. So V on the anywhere on the inside is going to be KQ over the radius of the ball, which is A. And so my work would be little q, which in my example is 2, times KQ over A minus KQ over R. Big Q in my example is this 20 microcoulombs over here. A in my example is 5 centimeters. Now, again, I'm going to make it 0.05 meters. And the radius, where am I starting at? That's 0.28 meters. So you plug those numbers in, you'd get the work term. Again, your numbers will be different, but this is the idea. Then we have number 12. Oh my. Okay, so about half of you got this one right. So I'm glad the half of you got it right, did that. It doesn't matter which path you take to go from A to B. It would be like saying the following. Let's say I had a desktop, all right, and I had a brick on the floor. And I said to you, you either take the brick and go from here to here, or you go from here to here, assuming you can go through the table there. Which one would have a bigger change in potential energy? Well, it's the same. All that matters is the start and end points. So your work to move from A to B is identical, okay, whether you go the path 1 or the path 2. All right, number 16 was next. Okay, let me scroll down here. So for number 16, they give you 2 different points, and they give you a field. And they say, what's the magnitude of the potential difference? Okay, so change in voltage is negative the integral E dot product dr. Now, in this case, the field's constant, so we don't have to integrate. So he gets negative E dot delta R. Okay, so you're just doing a dot product here. So it's negative. E was given as 3I plus 4J. We're dotting that with delta R. So now you got to figure out delta R. Well, the X coordinate goes from 1 to 8, so that's a 7. And the Y coordinate goes from a 4 to a 10, that's a 6. Okay, so then I got a negative out front here, which I'll worry about later. Okay, so then you just multiply your like things. So 3 times 7 is 21, plus 4 times 6 is 24. So for me, the magnitude of my change in voltage would be 45. Now, again, you're all going to have different numbers. For number 17 is the sign plus or minus. Well, I got a negative sitting out here, so it's minus. In other words, we're going with the field. The field points right and up. And we're moving 7 to the right and 6 up. So we're moving in general with the field. So because we're moving with the field, we're losing voltage. It's like flowing downstream. Remember, electric field lines are like flowing downstream. Okay. The next one, got 2 more to go. Number 18. Let's see, 20 of us got that right. Oh, by the way, this last one, number 16, only 14 people got that right. So only about a quarter of us. So don't know if we're forgetting dot product or what there, but that's something we can definitely work on. All right, number 18. 20 of us got that right, so it's only a third. This one involves, you got to be careful with your math here. So we have a positive 46 microcoulomb charge at the origin. I'll write 46 microcoulomb. Now again, you're going to have different numbers. And we have a negative 30 microcoulomb charge at 1.3 meters. Okay, so this is at 1.3 meters. They're going to move something from 85 centimeters, so that's 0.85, over to 0.35. Now, again, your numbers are all going to be different, but the process is going to be the same, okay? And what they're moving is a positive charge, and that is, they give it as 14 microcoulombs, okay? So we're going to use work equals Q delta V. The Q we're talking about is that Q there. So that's easy. The delta V is the part that takes a little effort here. So delta V, okay, well, I'm going to call this point A and this point B. And then I'm going to subtract them. So voltage at A. Well, I got two charges making a voltage at A. So I have K times 46. Now it's micro, so it's 10 to the negative 6. I'm not going to write that here, but when you're in your calculator, you would write that. Over, well, how far is it from that charge to A? Well, that would be 0.85. Plus, we got K times negative 30. And yes, you need a negative there. These are scalars. How far is it from that charge to A? Well, 1.3 minus 0.85 is 0.45. Okay, so you would get a voltage there. Now, again, these are both times 10 to the negative 6. Okay, don't forget that. So you'd get a voltage there. The voltage at B would be, the numerators would be the same. Okay, so I'm just going to rewrite those. What changes is our denominators. The second point, how far is that from the positive charge? Well, that's 0.35. And the second point is, the negative 30 is how far from that second point? Well, that's 0.95. It's 1.3 minus 0.35. You would get a second voltage there. Then you would calculate your change in voltage by doing the voltage at B minus the voltage at A. And that would be positive, by the way. And then once you got that number, you would plug it in right there, and you would get your work done to move that charge from point A to point B. So you had to find your two voltages at each point, and then you do work equals Q delta V. Okay. The final one that was missed frequently was number 21. Let me scroll down to that. So you get a charge, they give you a charge density in a cylindrical rod. So the rod looks like this. It's solid, it's an insulator, non-conducting. And it's got a radius, I'll call that R, of 8.7 centimeters. They want to know the potential difference from 3.6 to 5.7. So here's 0. We're going from 3.6 to 5.7. So the whole time we're inside that rod. Well, I'm going to use change in voltage is negative the integral E dot dr. Okay. Now, I don't know the E. Okay, so I'm going to draw my Gaussian surface right here. I'll just use that. Okay. And figure out the electric field by using Gauss's law. So Gauss's law, double integral E dot dA equals Qn over epsilon naught. So we got E, we want the lateral area of that cylinder, so it's 2 pi r. I'll give it a height h, okay, equals Qn. Well, that's rho times the volume of that cylinder. That's how much charge I capture. So the volume of that cylinder is pi r squared h, okay, all over epsilon naught. Now, I'm not going to plug numbers in yet. The pi's drop out, one of the r's drops out, the h drops out, and you get the electric field inside of there is rho times r over 2 times epsilon naught. So that's my electric field inside the cylinder as a function of r. And then I'm going to take that and plug it in here to integrate it. So delta V is negative the integral of rho r over 2 epsilon naught dr. And I'm integrating that from A to B. So I'll just write A to B here. Okay, we'll plug numbers in a bit. All right, so then you got negative, you got rho, the 2 and epsilon naught are constants. You're just integrating r, which becomes r squared over 2. If I tidy that up, this becomes negative rho r squared over 4 epsilon naught. Okay, evaluated from A to B. Okay, and so let's see. You would get negative. Let's see. The A would be positive, so you get rho A squared over 4 epsilon naught minus rho B squared over 4 epsilon naught. Now, when you do that, you're going to get a negative answer because B is bigger than A. Okay, so that answers question 22. This will give, when you'll plug your numbers in, again, make sure A and B are both in meters. That'll give you the magnitude, and again, make it a magnitude of positive. Also, another note, like why for 22 conceptually, how can you figure out negative? Well, it's given as a positive charge. So electric field lines point outward. Okay. And we are moving outward. So we're moving with the electric field lines. So if you're moving with the field lines, you lose voltage. Okay. All right. The rest of the questions went fairly well. I hope you found that video helpful, and thank you very much.